Last time we looked at the formulas that told us how we can take a trigonometric function of a sum of angles. We can use that same formula to figure out what happens when we take the trigonometric function of a multiple of an angle. So recall that sine of u plus v is equal to sine of u times cosine of v plus sine of v times cosine of u. So let's see what happens if we want to take sine of 2 times an angle theta. Well, 2 times an angle theta is, of course, just theta plus theta. And so sine of 2 theta is going to be equal to sine theta times cosine theta plus sine theta times cosine theta. And all we've done here is we've used the formula for the sine of a sum of angles and applied it in the situation where both those angles happen to be the same, happen to just be theta. So we get that sine of 2 theta is equal to 2 times sine theta times cosine theta. This is an example of what's known as the double angle formula, and the reason is that it tells us a relationship between a function of double an angle and functions of just that angle itself. This is another relationship we have that lets us move back and forth between expressions involving trigonometric functions by changing the angles inside, just like we did before with the sum and difference identities. And so we're going to have several of these identities that we work with. And just like with the sum and difference, we're only going to be looking at sine, cosine, and tangent because we can, of course, express everything in terms of them. So this is our formula for sine. Sine of 2 theta is always equal to 2 times sine theta times cosine theta. Interestingly, we use this identity and the other ones that we're going to talk about in both directions. Sometimes we've got a trigonometric function like sine 2 theta and we want to express it in terms of sine theta and cosine theta. Other times we might have an expression involving sine and cosine multiplied together, and that might be kind of complicated, and so we want to take that back and figure out when we want to express that using just a single trigonometric function. That can often be helpful for solving equations. So this is the double angle formula for sine. Cosine actually has 3 separate ones that we use. Now, the first one is based on the addition formula for cosine. So recall that we have that cosine of u plus v is equal to cosine u times cosine v minus sine u sine v. And therefore, we have that cosine of 2 theta is equal to cosine of theta times cosine of theta minus sine of theta times sine of theta. Or, to simplify this down a little bit, we have that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. So we've seen throughout the course that cosine squared plus sine squared of an angle always gives you 1, which is useful. We now also have the formula for what happens when you take cosine squared minus sine squared. You get cosine of 2 theta. We can manipulate this expression a little bit using the Pythagorean identity. Cosine squared theta minus sine squared theta can be written as cosine squared theta minus. Now, sine squared theta is the same as 1 minus cosine squared theta by the Pythagorean identity, which tells us that sine squared theta plus cosine squared theta is 1 for any theta. Rearranging this, distributing the negative through and gathering stuff up, we get that 2 cosine squared theta minus 1 is an equivalent expression. So we also have that cosine of 2 theta is equal to 2 cosine squared theta minus 1. If we do this the other way and replace cosine squared with 1 minus sine squared in this expression, then we get 1 minus 2 sine squared theta is also equivalent. This is an equivalent form, or an equivalent expression to cosine squared minus sine squared. So we also get that cosine 2 theta is equal to 1 minus sine squared theta. So there are our 3 expressions for cosine of 2 theta. And then we can do a similar thing with tangent if we use the formula for tangent of 2 theta. So let me summarize all these. On the next page, we'll get a table with just the formulas without any of the working out we did here. So we have the double angle formulas. We have that sine 2 theta is equal to 2 times sine theta times cosine theta. We have that cosine of 2 theta is equal to cosine squared theta minus sine squared theta, which is the same as 2 times cosine squared theta minus 1, which is the same as 1 minus 2 sine squared theta. And then we have the tangent of 2 theta, as it turns out, gives us 2 tangent of theta over 1 minus tangent squared theta. So those are what we've got, and so we can use them in order to work out the values of various angles. Now, it turns out that of all of our familiar angles, the 30 degrees, 45 degrees, 60 degrees, we already know what the sine, cosine, and tangent are of their doubles, because those other angles that we see are also familiar ones, multiples of 30, 60, and 90. However, when we've got an angle that's described in some other way, we can use the double angle formulas to figure something out about them. So let's let alpha be an acute angle such that sine of alpha is equal to 3/5. Find sine of 2 alpha, cosine of 2 alpha, and tangent of 2 alpha. So for this, we'll create a little triangle that will tell us about alpha, and that's going to be good enough to figure out the values of sine, cosine, and tangent of alpha. So because alpha is acute, we can use an actual triangle in order to measure it. And it turns out that if sine of alpha is 3/5, then that means that we can label the opposite side 3, the hypotenuse 5, and therefore the adjacent side is 4 by the Pythagorean theorem. Therefore, we have that sine 2 alpha is equal to 2 times sine alpha times cosine alpha, which is 2 times. We know that sine alpha is 3/5. We know that cosine alpha is 4/5, and therefore this whole thing becomes 24/25. So sine 2 alpha is exactly 24/25. Cosine of 2 alpha is equal to, and now we can use any one of these formulas that we've got over here. A lot of times the second or third ones are going to be easier because they just involve a single trigonometric function rather than a couple of them. So let's use the second one. Cosine of 2 alpha is 2 cosine squared alpha minus 1, which is going to be 2 times, now cosine squared, we said was 4/5, or cosine was 4/5, and then we square that. So 4/5 squared is 16 over 25, so that'll be 32 over 25 minus 1. 1 is 25 over 25, and so we get 7 over 25. And then tangent of 2 alpha will be 2 times the tangent of alpha over 1 minus the tangent squared of alpha. So this gives us 2 times tangent of alpha is 3/4. 1 minus tangent squared would be 1 minus 3/4 squared. And when you work all this out, you wind up with 24 over 7. Of course, once you'd figured out cosine of 2 alpha and sine of 2 alpha, you could also have just calculated the tangent of 2 alpha as the ratio of sine over cosine. So this is one thing that we use the double angle formulas for. Another thing that we use them for, as I alluded to before, is taking expressions that involve multiples of angles and writing them as expressions involving just the single angle inside. So let's take an example. Let's write sine of 3 theta in terms of just sine theta and cosine theta. Now, this, we can't use the double angle formula immediately on this. We have to use just the ordinary sum formulas. But we have that sine 3 theta is equal to sine 2 theta plus theta, because 3 theta is just 2 theta plus theta. And we can use the sum formula for sine. 2 theta, sine of 2 theta plus theta will be sine of 2 theta times cosine of theta plus sine of theta times cosine of 2 theta. And now we can use the double angle formulas, which of course were just built on the sum formulas to begin with, but they come up enough that they're worth memorizing on their own. So sine of 2 theta becomes 2 sine theta cosine theta. And then we have another cosine theta left over. And then we have plus sine theta. Now, cosine 2 theta, we have a few options here. And it really doesn't make a huge amount of difference which one we pick most of the time. However, I do notice that we've got in the expression on the left over here, I notice that we're going to have 2 cosines, and when we simplify down this left-hand part of the expression, we're going to get a cosine squared. So maybe in order to get as much cancellation as possible and simplify our life at the end, I will use the expression for cosine 2 theta, which involves a cosine squared. So we could write this as cosine squared theta minus 1, and therefore we can get 2 sine theta cosine squared theta plus 2 sine theta cosine squared theta minus sine theta. And now we can simplify further. The first 2 terms are like terms, and so we get 4 sine theta cosine squared theta minus sine theta. So deciding whether we want to use the expression we started with or the expression we ended it with very, very much depends on the context of the problem. Some problems you want to have as simple an overall expression as possible, and you're willing to have more complicated angles inside the functions. If that's the case, then you'll want to use the sine 3 theta. Sometimes you want to get all of your angles to have just, all of your functions rather, to have just thetas inside for one reason or another, in which case the sine 3 theta expression simply isn't going to work, and you have to convert it into the form that we have here, 4 sine theta cosine squared theta minus sine theta. So this is a way that we can use these formulas to simplify things down. As another example, let's try to solve sine 2 theta equals sine theta. We want to find all of the angles where if you evaluate sine at that angle and then sine at double that angle, you get the same thing out of it. Now, it's very, very difficult, basically impossible, to solve equations involving trigonometric functions of different angles. And so the fact that we have a sine 2 theta on one side and a sine theta on the other makes it almost impossible to do so. So if we want to solve the equation sine 2 theta equals sine theta, what we can do is first replace that sine 2 theta with 2 sine theta cosine theta equals sine theta. And now our expression is one that only involves sine of thetas and cosine of thetas, and we can try solving it in our standard ways. In this case, the thing we'll want to do is to subtract sine theta from both sides. So we'll get 2 sine theta cosine theta minus sine theta equals 0. We'll factor a sine theta out of it. So we get sine theta times 2 cosine theta minus 1 equals 0. And so here we'll get that sine theta equals 0, or 2 cosine theta minus 1 equals 0. And now each of these equations we can solve separately. So for sine theta equals 0, notice that if we look at the unit circle and we ask, well, where does sine equal 0? It's going to be at the points 1, 0 and at negative 1, 0, corresponding to angles of 0, pi, 2 pi, 3 pi, but also negative pi, negative 2 pi, negative 3 pi, so forth and so on. Basically, any half rotation around the circle from standard position will get you an angle with a sine of 0. So the solution to this first equation over here is theta is equal to pi n for n, any integer. Now for cosine theta minus 1 equals 0, or 2 cosine theta minus 1 equals 0, that means 2 cosine theta equals 1, which means cosine of theta is equal to 1/2, and we know that there are 2 such solutions within a, or 2 such angles within a single revolution around the unit circle. So if we've got triangles here with a ratio of 1 and 2, we're going to get ratios or side lengths of square root of 3 and negative square root of 3 on the other side, and we see that our 2 angles here are going to be pi over 3 and negative pi over 3. And so just as we did before with solving equations, we get two solutions out of this. Theta is pi over 3 plus 2 pi n for n an integer. And theta is equal to negative pi over 3 plus 2 pi n for n an integer. So in this problem, we get three families of solutions, multiples of pi, and then angles that are 2 pi, a multiple of 2 pi more or less than either pi over 3 or negative pi over 3. And that's how we can use the double angle identities to solve equations. One of the other important things that we do with the double angle identities is we use them to find the half angle identities. So let's look back on our double angle identity for cosine. We've got cosine of 2 theta is equal to, well, we've got a few different forms of it, but the two that I want to focus on are 2 cosine squared theta minus 1 and 1 minus 2 sine squared theta. Instead of thinking of theta as being the angle that we're sort of starting with, the one that we give a name to, we could also think of 2 theta as our starting point, sort of. So let's let alpha equal 2 theta. If we do that, that means, of course, that theta is alpha over 2, and we can rewrite these equations in a way that's completely correct still, which says that cosine of alpha is equal to 2 times cosine squared of alpha over 2 minus 1. And similarly, cosine of alpha is equal to 1 minus 2 sine squared of alpha over 2. Rearranging these, we get that cosine squared of alpha over 2 is equal to 1 plus cosine of alpha over 2. And we get that sine squared of alpha over 2 is equal to 1 minus cosine alpha over 2. Now, of course, we could also have rearranged it with the thetas to begin with, so we can also write our formulas using thetas and 2 thetas instead of alpha over 2's and alphas. The reason why I'm writing down all of these is because at various times and in various ways, each of them are helpful. We can use these in order to get the so-called half angle identities. So let me write these down, including the ones for tangent. The derivations for tangent you can find in the text, but it's just using the facts for sine and cosine. So the half angle identities are as follows. We have that sine squared theta is equal to 1 minus cosine squared of 2 theta. I'm sorry, not cosine squared, 1 minus cosine of 2 theta over 2, or equivalently, sine squared of alpha over 2 is equal to 1 minus cosine of alpha over 2. Those are 2 equivalent ways of writing down the same thing. Cosine squared theta is equal to 1 plus cosine of 2 theta over 2. And then cosine squared alpha over 2 is equal to 1 plus cosine of alpha over 2. tangent squared theta is equal to, well, it's the ratio of sine squared over cosine squared. So it's 1 minus cosine 2 theta over 1 plus cosine 2 theta. And similarly, tangent squared of alpha over 2 is equal to 1 minus cosine of alpha over 1 plus cosine of alpha. Now, one of the things that we can also get out of the half-angle identities, these forms, is expressions for just sine, cosine, and tangent of alpha over 2 if we take the square root. Now, the one thing we have to be careful of is we do get a plus or minus expression showing up. So we get that sine of alpha over 2 is equal to, if we take the square root of both sides, plus or minus the square root of 1 minus cosine of alpha over 2. Cosine of alpha over 2 is equal to plus or minus the square root of 1 plus cosine of alpha over 2. And tangent of alpha over 2 is equal to, it turns out we can actually do better through some algebraic manipulation, which is not too bad. We actually get that tangent of alpha over 2 is equal to simply 1 minus cosine 1 minus cosine of alpha over sine of alpha, which is in turn equal to sine of alpha over 1 plus cosine of alpha. This one doesn't come up quite as much, and again, you can find the derivation of this in the text. But we do sometimes use it. So let's use these formulas in order to compute the sine and cosine of something that we haven't seen before. Let's find sine, cosine, and tangent of 22.5 degrees. This is certainly not an angle that we are super familiar with, but what's going to help us out here is that 22.5 degrees is equal to half of 45 degrees. And so since we know about 45-degree angles, we'll be able to figure out what's going on for 22.5 degrees. So our solution, if we want sine of 22.5 degrees, well, here 22.5 degrees is behaving as alpha over 2, where alpha is 45 degrees. So, based on the formula before, we have that sine of 22.5 degrees is equal to plus or minus the square root of 1 minus cosine of 45 degrees over 2. Now, before we simplify all this down, we do want to consider whether we're looking at the positives or the negatives here, and this is where you want to use the quadrant that we're in. 22.5 degrees is in quadrant 1, so that means that sine of 22.5 degrees is positive. Whatever angle you're going to compute, the first thing you're going to want to figure out is what quadrant it's in so that you know whether to take the positive or the negative form of the equation you're looking at. So this is going to be the positive square root of 1 minus, and now we need cosine of 45 degrees. Cosine of 45 degrees is 1 over the square root of 2. And so our expression becomes this. Sine of 22.5 degrees is the square root of 1 minus 1 over the square root of 2 all over 2. Now this is a perfectly good expression, but we typically want to simplify it a little bit. We have inside the big square root, looking at the fraction inside, we see it's a complex fraction. We've got fractions on the top of the big fraction. So what we'll want to do is multiply the top and bottom of the inside fraction by the least common denominator of all the small fractions. If we multiply square root of 2 here, that's going to distribute across the top. Square root of 2 times 1 is the square root of 2. Square root of 2 times 1 over square root of 2 is 1. And then 2 times square root of 2, that's just 2 times the square root of 2. And that is a perfectly good expression for sine of 22.5 degrees. It's, again, not the sort of thing that we'd want to memorize, but it is good to know that we can do this. Similarly, cosine of 22.5 degrees will be the square root, positive square root, because we're in quadrant 1, of 1 plus sine of 45 degrees over 2, which is the square root of 1 plus 1 over square root of 2 over 2. So the only difference here is that we wind up with a square root of 2 plus 1 in the numerator instead of a square root of 2 minus 1 in the numerator. And then finally, tangent of 22.5 degrees, we know is 1 minus cosine of 45 degrees over sine of 45 degrees. We had that on the previous one. And so this would be 1 minus 1 over square root of 2 over 1 over square root of 2. Again, multiplying the square root of 2 in the numerator and denominator give us that this is square root of 2 minus 1 over over just 1. So we just get square root of 2 minus 1. So in fact, the tangent of this angle is a whole lot simpler to express than either the sine or the cosine, interestingly enough. So this is one of the main reasons why we use the half angle identities in order to evaluate angles like this. There are a couple of other places we use it, though. One of the main reasons is to reduce the powers involved. So, let's say we want to express sine squared theta times cosine cubed theta using only single powers of the trigonometric functions. And without any multiplication of trig functions. In other words, we want to write an equivalent form of this expression, sine squared theta times cosine cubed theta, where each term of the expression is only a multiple of, a constant multiple of a single trigonometric function. No sines times cosines, no raising to any powers, anything like this. There are a few ways that we will do that, one of the primary ones being the half angle identities that we had before, also sometimes known as the power reduction formulas. So recall that we're about to use these. We have that sine squared theta is equal to 1 minus cosine 2 theta over 2, and cosine squared theta is equal to 1 plus cosine of 2 theta over 2. So we're going to use that here. We've got sine squared theta times cosine sorry, I think I might have a typo here. We'll go forward and then we'll correct it if we need to. We have sine squared theta times cosine cubed theta. First thing that we want to do is to separate things up and group the powers together in groups of 2 because we see that our formulas here work with sine squareds and cosine squareds. Now sine squared theta we can reduce the power on, and we can take the sine squared theta expression and turn it into an expression 1 minus cosine 2 theta over 2 that has just a single trig function that isn't raised to a power. Now the angle inside that trig function is different. Instead of sine of theta, we have cosine of 2 theta, but sometimes that's what we want. Now cosine squared theta becomes 1 plus cosine 2 theta over 2. And I see I did in fact make a little typo here, so I really wanted in fact sine squared cosine squared. Sorry about that. Okay, so at this point we get 1 minus cosine 2 theta times 1 plus cosine 2 theta all over 2, and we've made some progress. Now let's try multiplying things out a little further. If we multiply these two fractions together, we'll get a 4 in the denominator. The numerator will take 1 times 1 is 1. 1 times cosine 2 theta is cosine 2 theta, but then we'll have negative cosine 2 theta times 1 is negative cosine 2 theta. Those will cancel out, and in fact, we'll just be left with minus cosine 2 theta squared. So we get 1 minus cosine squared 2 theta, which we can write as 1/4 minus 1/4 cosine squared 2 theta, because that'll be helpful for what we're about to do next. We've made progress. Our original problem had sine squared times cosine squared. It had four trig functions all multiplied together, 2 sines and 2 cosines. Well, now we have an expression with one constant term, which is fine, and one term that has a cosine squared. So we've made some progress. We're not done yet though, because we still do have that squared. But to continue the process, we're just going to apply the second identity over here, the half angle identity for cosine, again. Now, the thing to be careful of here is that in this formula, we start with cosine squared of some angle, which we've called theta in this problem, and then we wind up with double that angle in the formula here. So we always double the angle inside the trig function when we apply this power reduction style formula, going from a second power of cosine to a single power of cosine in this way. Here we're starting with cosine squared of 2 theta, which means that using the same identity, we'll have to change it into 1 plus cosine of 4 theta, because we always have to double the angle that's inside. Another way that can be helpful to think about it is just to rewrite our formula using a different variable. We could just replace this theta with alpha, and this is exactly the same formula. Cosine squared alpha is equal to 1 plus cosine 2 alpha over 2, and we can just let alpha be 2 theta. If we let alpha be 2 theta, then we get that cosine squared of 2 theta is 1 plus cosine of 4 theta over 2. So we're almost done now. We just have to simplify things down. So we get 1/4 minus 1/4, and again, I'm going to split up the inside. We get 1/2 plus 1/2 cosine 4 theta Sorry, I'm running a little bit out of space. So we get 1/4 minus a fourth times a half is minus an eighth. That minus a fourth times a half is minus 1/8, and then cosine 4 theta. 1/4 minus 1/8 is 1/8, so we wind up with 1/8 minus 1/8 times cosine 4 theta, and we have accomplished the problem. We have taken the original expression, sine squared times cosine squared, after I corrected the typo, and we've seen that that can be written using 1/8 minus 1/8 cosine 4 theta, and they're completely equivalent. It turns out this particular process is very important when you are going to do certain things in calculus. There are certain types of operations that you do in calculus, certain types of problems that you want to solve, where changing the angle inside the trig function is very easy to accommodate for. It's very simple to handle the inside of the function being 4 theta instead of theta. But raising to powers and multiplying things together is sometimes much harder in those types of problems. And so this simplification process is one that is very, very important in calculus. All right, the last thing I want to do is to see how we can use the half-angle identities to get a formula for the area of an isosceles triangle. So let's ask, what is the area of an isosceles triangle with sides of length A on either side of an angle theta? So the answer to this problem will obviously be a formula in terms of A and theta, because the answer will depend on those. So we're told we have a triangle, like this. A theta. It's an isosceles triangle, and we want to know what its length is, or what its area is, rather. Now, the way that we can do that is by constructing a right triangle, or a couple of right triangles, actually, out of this. So let's look at what happens if I drop a line down here that's going to make a right angle with the base of the triangle, and you can show by the various congruence theorems from geometry that in fact the two smaller triangles inside the isosceles triangle are congruent, and in particular that means that these two angles are going to be the same. So now let's let B be the height of the length rather of the green segment right here, and let's let C be the length of these two half sides, the two sides of the small sides of the two small triangles. So we know that the area of the big triangle is going to be 2 times the area of the small triangle, which is 2 times, and now we know that the area of a triangle is 1/2 times base times height. In this case, that's 1/2 times B times C, because B and C can be thought of as the base and height of the two small triangles. So, in fact, it's just B times C. So really what we want to be able to do is express B times C in terms of A and theta. So let's think about this. Let me redraw the small triangles that we're working with. We have BC. This angle up here is theta over 2, and the side length A. Remember, A is a given quantity. We want to express things in terms of A and theta. So, remembering how we do this, relating the things that we are given, A and theta, to the things we're trying to find, B and C, we can see that we have that cosine of theta over 2 is equal to B over A, which means that B is equal to A times cosine theta over 2. And then we also have that sine of theta over 2 is equal to C over A, which means that C is equal to A times sine of theta over 2, which means that B times C is equal to A to cosine theta over 2 times A sine theta over 2. All right, that is A squared times sine theta over 2 times cosine theta over 2. So that gives us an expression. Now there are a couple of ways that we can go here. One that's a little bit simpler. It doesn't require as much cleverness to spot, but takes a little bit longer to do, and one that is very, very quick, but takes some cleverness to spot. Let's do it both ways. We want to find a simpler form of this expression, A squared sine theta over 2 cosine theta over 2. Let's get ourselves a new page to do that. So we got A squared times sine theta over 2 times cosine theta over 2. Well, one thing that we can do is just use the half angle identities. We know that sine theta over 2 is going to be the square root of 1 minus cosine theta over 2. And cosine theta over 2 is going to be the square root of 1 plus cosine theta over 2. In this case, we've taken the positive form of the square roots in both cases because everything inside here is acute. Theta over 2 is going to be an acute angle because theta itself can be has to be less than 180 degrees. So theta itself has to be less than 180 degrees. So that means that theta over 2 has to be less than 90 degrees. In other words, theta over 2 is acute, which means that sine and cosine of theta over 2 are both positive. Well, now we can do some algebra. This gives us A squared times the square root. We can multiply the two together. We get 1 minus cosine theta times 1 plus cosine theta all over 4. This simplifies to A squared times the square root of 1 minus cosine squared theta over 4, because when you multiply these together, the two middle terms in the distribution cancel out. So we get A squared times the square root of sine squared theta over 4. We can go from 1 minus cosine squared to sine squared by the Pythagorean identities. Now, A squared then gets multiplied by the square root of sine squared gives us the absolute value of sine. And the square root of 4 gives us 2. The square root of x squared is always the absolute value of x. And so we want to put the absolute value of the sine there. However, again, we know that theta is an interior angle of a triangle. Therefore, it has to be between 0 and 180 degrees. And therefore, sine of theta has to be positive. We don't know about cosine. Cosine of theta could be positive or negative, but sine of theta is positive because sine is positive in quadrants 1 and 2, where theta has to live. And so that means that the absolute value of sine theta is just sine theta itself. So our result then is 1/2 a squared sine theta. And so this is the area of an isosceles triangle with two sides of length a and an angle of theta in between them that we got using our half angle formulas. However, there is a simpler way, as I mentioned, using the double angle formulas. And the thing that tips you off that it might be useful is that you got a sine times a cosine with no other powers or anything involved and with the same angles in both of them. And the reason why this is something that you want to watch out for is the following. Remember that sine of 2 alpha is equal to 2 times sine alpha times cosine alpha. This was our double angle formula for sine way back at the beginning. A very useful form of this is the following. If you ever have sine alpha times cosine alpha, you can always write this as sine of 2 alpha over 2. We've just divided both sides by 2. Which means that a squared times sine theta over 2 cosine theta over 2 is equal to a squared times sine of theta, because theta is 2 times theta over 2 divided by 2. So this is just using this right here, and so we immediately get to 1/2 a squared sine theta. So by recognizing when we've got something that's part of the double angle formula for sine, we can often make very quick work of problems that would otherwise be more time consuming. So I'll just write down as our conclusion to this problem that the area of an isosceles triangle with two sides of length A with an angle theta between is 1/2 a squared sine theta. This works out to be surprisingly useful in many different contexts.